we are discussing non-linear fiber optics. In the last lecture, we saw that when the light intensity increases, the higher order susceptibility terms in the induced polarization of a dielectric material have to be taken into consideration. We also saw that for a material like glass, the second order susceptibility contribution is negligible. So, the non-linearity primarily is because of the third order susceptibility, which leads to what is called the Kerr non-linearity. So, we show that the polarization has these terms here. This is the dominant term which contributes to the dielectric constant, and that is the term which contributes to the non-linearity. So, for the Kerr non-linearity, the refractive index of the material has a term which is proportional to the square of the electric field or the power density in the material. So, essentially we are investigating the pulse propagation inside an optical fiber in the presence of this non-linearity. Then starting with the simple Maxwell's equations and defining a function which has a cross sectional field distribution and a pulse which is evolving in the direction of propagation z. We wrote the wave equation in the spectral domain around frequency omega 0, and then we got these two separate equations, one which governs the transverse distribution of the field, which is this function f, another one is the evolution of the pulse envelope, which is given by this in the direction of the optical fiber. We also saw that since the evolution of the pulse is slow, the second order derivative of A as a function of z can be neglected. So, you have a simple first order differential equation for the evolution of the pulse, whereas for the transverse field distribution you have this equation. Now, note here that this equation is exactly identical to what we have already solved when we investigated the field propagation or the modal distribution inside the optical fiber. So, when the nonlinear effects were not present, essentially this envelope function we had not taken, we simply had seen that the electric field is given in terms of this transverse field distribution and the phase function, at where beta 0 is the phase constant at frequency omega 0. So, we are assuming here that even in the presence of nonlinearity, the modal field distribution is practically unchanged. So, that means, if I consider let us say LP01 mode or HE11 mode, that distribution is more or less same, whether we include nonlinearity or we do not include nonlinearity. Only thing is, this field distribution will evolve as this field distribution would start propagating along the optical fiber, which is given by the second equation. So, our focus is only on this equation, the second equation, because this equation we have already solved, and we know the solution to this equation comes in the form of Bessel functions, the modified Hankel functions, we apply the boundary conditions and so on and so on. So, let us focus now primarily on this equation and see what more we can do, how can we simplify this and get some more simplified version of this equation and see physically what different terms mean in this equation. So, first of all, since this quantity beta tilde, which you see here, this quantity, since this is a very close to quantity beta naught, because we are talking about a narrow band frequencies, one can make a approximation to this. So, one may say first of all that this square minus beta naught square, this approximately, let us say first do not make approximation, this is beta tilde minus beta naught, beta tilde plus beta naught. And since this beta tilde is very close to beta naught, we can say that this quantity is almost same as beta naught. So, we can say that this is approximately equal to 2 times beta naught, which is this term, times beta tilde minus beta naught. So, I can take this thing now and substitute into this equation. So, this quantity here we can say 2 times beta naught into beta tilde minus beta naught. So, 2 beta naught will cancel, and then this equation will be modified to by d z plus j beta tilde minus beta naught a, which is equal to 0. Now, since we are having a band of frequencies, the beta is not same as beta naught everywhere, but there is a small change with respect to this beta naught, because we are having a band of frequencies. So, what one can do is one can sort of have a Taylor series expansion to get a value of beta around beta naught in terms of the derivatives of beta naught as a function of omega. So, we can say that this quantity beta is a function of omega, that is equal to beta naught, which is beta at omega equal to omega 0, plus omega minus omega 0 d beta by d omega at omega equal to omega 0 plus omega minus omega 0 whole square upon 2 d 2 beta upon d omega square, again at omega equal to omega 0 plus and so on. For the brevity reason, if we say that this beta n is defined as d n beta divided by d omega to the power n at omega equal to omega 0, then this quantity can be denoted as beta 1, this quantity here is denoted as beta 2 and so on. Now, the dielectric constant of a medium, as we already said, is having a linear and a non-linear component. So, the epsilon for the medium is given as n, which is the function of omega, plus the delta n whole square. Yes, we know from our very basic relation that the epsilon is now equal to the refractive index square. So, this one we can approximately say is equal to n square plus 2 n to delta n. Here again we are assuming that this delta n term is negligibly small. So, the second order terms can be neglected, we retain only the first order term of delta n. And this delta n, as we have seen earlier, this is because of two factors now. One is because of non-linearity, which is given as this, and the loss term, because we have seen that the first order susceptibility is complex. So, you have a imaginary term which is minus j alpha divided by 2 times k naught. So, you have the refractive index, which is for a dielectric constant considering only first order susceptibility without the loss term, and then you are having a small contribution which is coming from non-linearity and the loss in the material. So, this quantity in this now, this quantity beta tilde as a function of omega, we can write as beta omega plus a small change in beta omega because of these terms. So, delta beta omega. And the delta beta omega can be obtained essentially from this, which is given as delta beta omega, that is equal to k naught square n omega divided by beta omega integral of delta n is a function of omega, the field distribution square delta omega, where this is the cross sectional area divided by integral f d omega. F square. If we now define the inverse Fourier transform for the envelope, so I say this is A, now z of t, which is equal to 1 upon 2 pi minus infinity to infinity, A tilde, which is the envelope function as a function of z and frequency, e to the power j omega minus omega naught t delta omega. And substitute now this into this term, this equation here, or this equation here, which we have got from all various terms after expansion and so on, we get a equation in terms of this A, which is in time domain, as dA by dz plus beta 1 dA by dt minus j beta 2 upon 2 d 2 A by d t square plus alpha upon 2 A equal to minus j gamma mod A square to A, where this quantity gamma, which is the non-linearity parameter, and that is related to the change in refractive index because of non-linearity, this quantity n 2, the non-linearity coefficient, and also the confinement of the light. So, where this quantity here gamma, which you get, is n 2 omega 0 divided by C into A effective, that is the effective area over which the light is confined inside the optical fiber. And when you do this algebra here, this quantity A effective, which you get, that is given as integral of f square d omega whole square divided by f to the power 4 d omega. So, if I know the transverse field distribution of the mode propagating inside the optical fiber, we know this quantity f. So, essentially by substituting this expression, we can get the effective area over which the light is confined inside the optical fiber. And once we get that parameter, then one can substitute into this. I know the non-linearity coefficient for glass. So, we can calculate this parameter gamma, which is a non-linearity parameter. Now, the typical value for the effective area inside the optical fiber may range from about 1 to 100 micrometer square, depending upon what is the core size and what field distribution you are taking, and so on and so on. And the corresponding value of this parameter gamma may be in the range of 1 to 100 watts minus 1 per kilometer. So, this is the equation finally which has evolved now, which tells how the A, which is the envelope function, is going to evolve as the pulse travels on the optical fiber. Now, let us look at the various terms here and let us try to get a physical meaning, what they are actually representing, these terms here. So, let us take the first simplest possible term. Let us say that beta 2 is negligibly small. Let us say this quantity is not there. Let us say there is no loss. So, alpha is also equal to 0, and let us say there is no non-linearity also. So, even this quantity is equal to 0. So, if I neglect this term, if I neglect this term, if I neglect this term, then I have got this quantity which is dA by dz, which is equal to minus beta 1 dA by dt. So, from there essentially we get dz by dt, which is equal to 1 upon beta 1, and that is what we know, that what does this quantity d omega by d beta represent? We know that d omega by d beta represents the group velocity of the signal. That means, it is the effective velocity of the pulse on the optical fiber. So, essentially d beta by d omega, which is beta 1, that is nothing but 1 upon the group velocity. So, this quantity, as you have seen here, this is 1 upon the group velocity. So, what this thing is simply saying, that if the loss was neglected, if this quantity is neglected, if non-linearity is neglected, then you have got a simple equation which is this, which is simply saying that the velocity of the pulse is equal to group velocity, right. That is what the simple thing we can get. Let us say we consider now a situation where we are moving with the pulse. That means, if I just take a situation where the pulse is not stationary, but pulse is moving, and that is moving with velocity which is the group velocity. So, we move with the group velocity. So, if I talk about now a new time reference, which is in the moving time frame, a frame which is moving with group velocity along with the pulse, then it is obvious that this term essentially has to go to 0, because then there is no question of velocity, because we are seeing now we are actually riding the pulse, we are measuring all the times with respect to that moving frame, which is respect to that pulse. So, this term essentially goes to 0. So, first thing what we can note is that if I define a new time frame, let us say I define a new time t, which is the old time t minus z divided by V g, which is same as t minus beta 1 times g. And what is beta 1? As you have seen, beta 1 is equal to 1 upon group velocity. So, this term here beta 1 times d A by d t that you can write as beta 1 dA by dt times dt by dt. And from here you can write as this is beta 1 dA by dt into 1 minus dz by dt, which is nothing but group velocity. So, you got here beta 1 times V g. But beta 1 times V g is equal to 1. So, this quantity 1 minus 1 is 0. That means, this quantity, if I take this equation in the new time frame, which is this capital T, this quantity will be equal to 0. So, what that means is now that we can substitute now this in this equation the new time, and in that time this term will not be there. You will have all other terms, but this term will vanish. So, we will get the new equation now, which is dA by dz minus j beta 2 by 2 d 2 a by d capital T square, which is the time measured in the moving frame, plus a by 2 a is equal to minus j gamma mod a square into a. This equation resembles the Schrodinger equation. Therefore, this one in the nonlinear fiber optic terminology, this equation is referred to as nonlinear Schrodinger equation. Or in short, it is written as NLS. So, the pulse evolution on the optical fiber essentially is governed by this equation, which is an approximate form of the wave equation for evolution of the pulse. So, two things to note here. What we have done is we started with the wave equation. In the wave equation, we made certain approximations. We assume that the transverse electric fields or the magnetic fields, transfer field distribution, is practically same as what was there in the absence of nonlinearity. Only when this field distribution travels along the optical fiber, the envelope undergoes an evolution, and this nonlinear Schrodinger equation gives the behavior of that envelope as a function of distance on optical fiber. So, essentially now if you want to study the evolution of the pulse in a comprehensive fashion, we have to look for the solution of this nonlinear Schrodinger equation. However, before we get into that, let us first try to understand what these different terms in nonlinear Schrodinger equations are representing. So, first of all, let us take the simplest term, which is this term here, which is alpha by 2 into a. So, let us assume that the beta 2 is negligibly small, nonlinearity is not present, and I have an equation which is simply dA by dz plus alpha by 2 a, that is the equation which I am having. So, in the simplest form, let us say assuming beta 2 is negligible and no nonlinearity. that is gamma is equal to 0. In this situation, then one can get an equation which is simply d A by d z, which is equal to minus alpha by 2 into A. So, solution to this equation is very simple, that the A as a function of z is at some initial location A 0 e to the power minus alpha by 2 into z. And as we know, the alpha, as we have taken, is the attenuation constant on the optical fiber. It simply says that this pulse, whatever we are launching, is going to exponentially die down, right, with this attenuation constant alpha. It is like a typical medium which has a loss alpha. The signal, when it propagates on the structure, it exponentially dies down with the attenuation constant. That is what a simple solution which you get. So, this term here, this quantity here, is representing the loss into the medium, and if other effects are absent, then you have a exponential decay of the signal on the optical fiber. So, this term corresponds to simple loss term. This term, as we already said, depends upon the nonlinear coefficient. So, this one is coming because of nonlinearity. What is this term representing now? This term, as we can see, is proportional to this quantity, which is beta 2. And what is beta 2? Beta 2, as we have already seen, is d 2 beta upon d omega square. That means, that is the derivative d by d omega of d beta by d omega, and d beta by d omega is nothing but the group velocity. That means, this term is telling you the change in group velocity as a function of frequency. That means, different frequencies are going to travel with different velocity, different group velocity, and that is what actually is captured by this quantity here. And what is that phenomena? The different velocities travel with different group velocities. That phenomena is nothing but dispersion. The dispersion is defined as the different wavelengths are traveling with different velocities. So, we have seen already different types of dispersion. We have seen dispersion which could be just intrinsically because of material properties. That means, the refractive index changes as a function of frequency. So, different frequencies travel with different velocity, or it could be because of different modal propagation. But essentially, when different modes are not there, if the fiber is simply single mode, then the different frequencies are going to travel with different velocity, which we call as a monochromatic dispersion. That is what actually is captured by this term here. So, this term in this equation essentially represents the dispersion. So, now what we are saying is that this nonlinear Schrodinger equation which we have got, it takes into consideration the effect of dispersion on the pulse evolution, it takes into consideration the loss on the optical fiber, and it also takes into consideration the nonlinear effects, right, on the evolution of the pulse. So, normally if you really look at this equation, to solve this equation complete is quite a tedious task. You require numerical methods to really solve these equations. But in principle, essentially what we can do is, one can define these two operations. You see, this is the operation which is going to take place, right, into say second derivative of time, and this can be easily done if I take the Fourier transform this equation, forget, let us say integrate these two quantities, then you will see that solving this equation, the Fourier domain is much easier, because the second derivative in time, right, is reduced to simply multiplication of the frequency square. So, if I look at the phenomena of dispersion, that can be easily investigated in the frequency domain, because different frequencies are traveling with different velocities. If I look at this phenomena, which is the non-linearity phenomena, then that has to be considered only in time domain, because this quantity depends upon this mod A square, and A is an envelope function in time. So, if you want to solve this equation has to be simultaneously solved in frequency and time. However, since both these effects are rather weak effects, one can solve, while solving this, one can assume that when the dispersion is playing a role, the non-linearity is negligible. When non-linearity is playing a role, the dispersion is negligible, and considering the effect of one at a time, one can essentially understand the evolution of the pulse. So, what one can do is, now for numerically solving this problem, one can define the two parameters or operators. Let us say define a dispersion operator. Let us say define that as some d cap, that is equal to j beta 2 by 2 d 2 by d t square minus alpha upon 2. And you define a non-linearity operator let us say n cap, that is defined as minus j gamma mod A square. And as we already said, applying this operator in frequency domain is easier, and applying this operator in time domain is easier. So, now the evolution of the pulse now can be studied by using what is called a split Fourier step method. So, here what we do is, we have a medium on which we want to study the pulse evolution. Let us divide this into the small sections. So, let us say we divide this into these sections here. So, let us say this size is some delta z, over which we assume that the effect of non-linearity and dispersion both are small, and it may be adequate to consider one effect at a time. So, what one can do is, one can solve this equation by applying this d operator, assuming that the non-linearity is not present. So, let us say I take half of this step. From here to here, I apply the operator which is d cap. So, the spectrum is modified because I am doing in frequency domain. Take a Fourier transform, come in time domain and apply this operator at this location. Let the pulse evolve again for this distance which is d cap, then apply again the n operator. So, in this region you are solving the wave equation in the Fourier domain, in the spectral domain. So, you get a spectrum. When the spectrum is there, you come at this location, you take a Fourier transform, you got a time function. Once you get a time function, you apply in time domain this operator, because now time function is known. So, this quantity is known. So, I know this operator now. So, I can find out what thing have to be applied. So, I applied this quantity here. Whatever new function I got, I take its Fourier transform back, go to spectral domain, again apply this operator, and you go on doing it repeatedly over this. So, that you get the evolution pulse on the optical fiber. So, that is the way this will be numerically solved though for certain specific kind of pulse shapes you may get analytical solutions, right, if you consider the things one at a time. But if you consider a general complex pulse function, then essentially it has to be solved by numerical techniques and by applying the operator sequentially, right, over the small steps, and then finding out how the pulse evolution is going to take place. So, that is what is the basic formulation for getting the solution of the wave equation in the presence of nonlinearity, right, on an optical fiber. What one can do is one can now define certain parameters which characterizes these three quantities. What one can do is one can define some two parameters which sort of characterizes the length over optical fiber related to dispersion and the nonlinearity. So, let us consider now a situation for a Gaussian pulse propagation. So, let us say I take a pulse which is Gaussian, and this pulse is having the sigma which is given by T naught. So, you have a standard deviation for this Gaussian which is given as T naught. So, the pulse Gaussian pulse let us say A is a function of t is given as e to the power minus t square upon 2 t naught square. Then for this pulse we can define the characteristic lengths on optical fiber. So, one can define the two characteristic lengths. One is what is called the dispersion length, and that is defined L d, which is equal to T naught square divided upon mod of beta 2. One can define the characteristic length which is called the non-linearity length, which is L and L, and that is defined as 1 upon gamma into P, where P is the pulse power and gamma is the nonlinearity parameter as we have defined in the nonlinear Schrodinger equation. So, once you define these two characteristic lengths, then the solution of this nonlinear Schrodinger equation can be approximated depending upon the situation of the pulse propagation on the optical fiber. So, there may be various possibilities that if I consider a physical length of optical fiber over which the propagation is taking place, this physical length could be much smaller compared to this quantity, could be much smaller compared to this quantity, could be much smaller compared to this, but much larger compared to this, right, or much larger compared to this, much smaller compared to this, and vice versa. So, essentially you have four combinations, that if I consider the physical length L of a fiber, and for simplicity let us assume that the loss is negligible, loss is not playing any role. So, for physical length L on a fiber with let us say alpha is approximately 0. You may have three main possibilities or let us say four main possibilities. One is this length L. So, situation 1, is L is much less than L d dispersion length, L is much less than L and L also. So, firstly, what is this two length they are telling us? This length is telling us that over this distance the dispersion effect becomes significant. The L and L is the length over which the non-linearity effects are significantly observed. So, if I can consider a situation that the physical length or the propagation length is much less than L d, that means the length is not enough even to observe the dispersion effect. L is much smaller than L and L also, that means the length is not enough to even see the non-linear effects. So, in this case the optical fiber becomes a simple bare medium of transportation of pulse from input to output. So, there is no modification of pulse either in the spectral domain or in time domain. The same pulse whatever you are launching essentially appears on the other side. So, in this case the fiber is a bare medium, just a medium to transport light. The signal does not undergo any modification at all. Right. The second possibility, as we said, is that L is much greater than L d, but L is still much less than L and L. When this situation occur, that if you consider a very narrow pulse, right, in that time this L d will be small. So, the pulse will be travelling over a distance which is much larger than L d, that means dispersion effects will start seen on the optical fiber, but the power in the pulse is still not very large. So, nonlinear effects are still not seen. So, in this case what you will see? You will see what we have been discussing in the optical communication so far, that you will see the pulse broadening phenomena or the dispersion phenomena. So, in this case you will see dispersion of the pulse or pulse broadening, and this regime then we call is the group velocity. Limited regime. Or GVD limited regime. So, normal optical communication, when we talk about, normally most of the time this is the situation that the length is much larger than L d, but nonlinear effects are not significant and you see pulse broadening, right, of the on the optical fiber. Third possibility is that L is much smaller than L d, but L is much larger than L and L. When will that happen? That will happen if I consider a reasonably broad pulse, so that the L d is large, where L d is proportional to T naught square, but the power in the optical pulse is large enough, so that the nonlinear effects are really observable. When I do this, that time we see a situation what is called the self phase modulation. And we will discuss this phenomena in detail little later, but what it is simply saying is, now the pulse broadening is not taking place because of dispersion, but I am having a pulse and this pulse is going to see the different refractive index at different location. So, within the pulse the frequencies are going to travel with different velocities, and which creates some kind of the phase function. So, the pulse has a tendency to modify itself in phase function, because the refractive index is a function of the pulse shape. So, this phenomena is what is called the self phase modulation, because this self phase, the modulation of the phase is taking place because of the pulse itself, because the pulse intensity is going to modify the refractive index. This refractive index is going to change the velocity of light, and different frequencies will travel with different velocities, and as a result you will see there is some kind of a variation of phase within the pulse itself. So, this phenomena is what is called the self phase modulation. So, in this regime what we call as a non-linearity limited regime, we see the phenomena of what is called self phase modulation, or in short it is called SPM. The last case, that the pulse is narrow enough. So, L is much greater than L d. So, dispersion is showing effect, L is also much greater than L and L. The power is large enough, so that nonlinear effects are also visible. Now, you will see the interplay of the dispersion and nonlinearity both, and that in that situation we get a very special kind of propagation, what is called solitonic propagation. So, this will give solitons. So, what we will do when we meet next time? Essentially, we will take one by one. This case of course is very simple. This we have already investigated in great detail when we talked about just the simple optical communication. So, we do not have to investigate this case. We will investigate this case, which is the dispersion limited regime. So, we will say the nonlinearity is not present, and then see what way the pulse evolves, what happens to the internal structure of the pulse, and so on and so on. Then we take the second case, when we say that the dispersion is negligibly small, only self phase modulation is there, and then we will see how what happens to the pulse, right, as an envelope, as an internal structure, as a frequency spectrum, and then we will see when both are present, what will happen to this pulse. So, essentially taking one by one, then we will have a complete comprehensive understanding of the evolution of the pulse on the optical fiber, and that will eventually lead to what is called the solitonic propagation on the optical fiber. So, let us summarize what we did. We started with the wave equation. We define the fields which are having transverse distribution, which is same as what the fiber has in the absence of nonlinearity. But now the field distribution has an envelope function which evolves as this function travels along the optical fiber, and then we got, after making certain approximations, then we got an equation what is called a nonlinear Schrodinger equation. The nonlinear Schrodinger equation is a comprehensive equation, because it takes into account the loss in the optical fiber, the dispersion into the optical fiber, the nonlinearity into the optical fiber, right, and also the group velocity of the pulse on the optical fiber. Then by using simple coordinate transformation defining the time in the moving frame, we got rid of the term which corresponded to the group velocity term, and then we got the nonlinear Schrodinger equation with the terms with nonlinearity, dispersion and the loss. And then we also saw that we can define certain characteristic parameter corresponding to the nonlinearity as well as dispersion, and then depending upon the physical length compared to these characteristic lengths, you may see different phenomena on optical fibers. You can either see dispersion, which is pulse broadening, you can see self phase modulation, which is because of nonlinearity, and also a phenomena which is interplay of these two, which will lead to what is called the solitonic propagation.